So thank you for being with us this morning. I will quickly introduce Safran Data Systems, and I will switch then the floor to my colleague, Ghislain Guerrero. So Safran Data Systems, we are known around the world to provide ground stations for everything related to satellite or to scientific missions. We are providing antennas, RF equipment, and special modems which are linked to the command control of the satellites for having accurate positioning of the satellites and also collecting data from payload. What we will focus on today is definitely aerospace testing, for which we are providing both airborne equipment and solutions, and also ground equipment and solutions, which will allow all the users to save time, avoid mistakes, and so on in the processing of their flight test. It's not working anymore. So I will introduce Ghislain Guerrero for the presentation of wireless instrumentation, application to rotary wing. Thank you, Ghislain.
Thank you, Noel. Good morning, everyone. So this presentation will focus on a short overview of flight test instrumentation for rotary wings and what is our history in this field as Safran Data Systems. And now we will focus on one particular project, which is called IRIS, in the scope of the European project called RACER. And then we'll open up a little bit with what we have in our roadmap for this domain. So first of all, fixed rotary wings can cover a wide range of applications from small eVTOLs to small civil or military helicopters, or even heavy ones. So under this name of rotary wings, there's a lot of challenges that we can encounter depending on the size of your vehicle. Nevertheless, we can just maybe define what is a typical flight test installation for a rotary wing. Typically, we encounter data acquisition units that are spread everywhere in the helicopter, mainly on the rotors and also on the main fuselage. And the purpose of these units is clearly to collect the data from the various sensors or buses available in the vehicles. Then all these measurements acquired by these devices are merged, sent to a switch, typically an Ethernet switch, in order to merge all these data and then to distribute them to different data sinks that exploit this process and these data. Among them, you have a display usually on board the pilots or the flight test engineer that is flying in the vehicle is monitoring some critical parameters. And so there's these parameters are displayed directly in the cockpit, and the idea is it's a subset of everything that is collected and focusing on the critical aspects for the safety of flight, but also for validating the different test sequences. All the data acquired are sent to a recorder that collects everything for post-processing aspects, and a subset also of data is sent to the ground, because typically on these kind of vehicles, all the specialists for engine, aerodynamics, structural aspects, and so on, are not flying in the test vehicles, they are on the ground. So all the data are sent through a transmitter to the ground. So these are the main components, and this is a typical architecture that can be, of course, scaled depending on the size of the helicopter. That's what you can have in mind. Next. Next. Oops. Okay. Something very, of course, unique and specific of the rotary wings application is, of course, the instrumentation of the rotors that are very specific. And in this field, we encounter in this type of vehicles many different kinds of rotors. First of all, the main rotors, but also the tail rotors. Sometimes they also encounter coaxial rotors, contra-rotary coaxial rotors. So all of this brings a lot of challenge for the instrumentation of these parts that are also critical for the performance, the overall performance of the vehicle. The number of acquisitions that we have in this field, when it's typically a tail rotor, can be dozens of acquisitions, measurements. But on the main rotor, typically it can go up to 100 of channels of measurements that have to be performed. They are of different kinds of measurements. They can be mainly, there are strain gauges, but also we encounter accelerometers, pressures, positions also, and sometimes video also that are directly, the recaptures that are directly performed on the rotor, typically for icing, de-icing tests, but not only. The rotation speeds are very different from a rotor to another, a kind of rotor to another, or a kind of application. It can start at 400 something, 450 RPM, but can go up to 3000 RPM. So this brings a lot of challenge, and this is really dedicated to the size, in fact, of the rotor. The smaller, the faster. And there are two main solutions today to transmit data from the rotors to the fuselage, slip rings and wireless aspect that we'll see on the next slide. So slip rings is clearly the legacy way to capture and to transmit, measurements from the rotating part to the main fuselage, the stator part. And this works quite well. That works well for decades. And in fact, two options can be used for these slip rings. First one is to directly connect the sensors to the slip rings and to transmit through the slip rings the analog signals to the rotors. This is very simple, minimal setups. You have just the minimal sensor set and wires on the rotor, so it's not very intrusive. But the counterpart of that is the fact that you have a limited number of channels because you have to pass through these slip rings many lines, analog lines, and usually the measurements are very noisy. They are affected. The performance of these measurements are not that good. And whatever you do with the slip rings, even if you are on the second options with having the DAU that digitize the measurement directly on the rotor, and then the transmission on the slip ring is a digital communication. Even in this case, you have a very big constraint of maintenance when you need to change these slip rings, and when it reaches its end of life, you have to remove the complete, dismount the complete rotor, and that's a very heavy operations that takes a lot of time during the flight test sequence that is always critical in this respect. So the second option is to use wireless data transmission from the rotary part and the stator part. And there are two main categories, the inductive transmissions and the radio ones. Inductive is also very simple, works very well from decades now, but and also the interesting thing with the inductive aspect is the fact that you share the same antennas as the power transmission, that is also wireless. But usually you have a limited bandwidth, and what we have encountered in the past is the fact that there's no real synchronization or accurate synchronization schemes or techniques between the static part and the rotary part. So the measurements are not that much synchronized. It's difficult to correlate measurements from the rotors and the one performed on the static parts. The second one is using radio transmissions, and many different solutions exist on that. But it's always quite tricky because of the masking aspect of the blades, and usually it has some counterpart in terms of bit error rate. So somehow disponibility of the measurements and the overall accuracy that is available, and also the synchronization. If you want to have an accurate synchronization between the stator part and the rotary part, in this case, you need usually a dedicated bidirectional communication. And the radio transmission does not cover today the powering aspects of this transmission, so you need something in addition. So briefly, so Safran Data Systems has been instrumenting rotary wings for decades. And we have many platforms on which our equipment, typically our MDR, modular data recorder, which is a DAU plus a recorder integrated together, has been mounted on many different platforms. And also, we can mention that we have provided to Copter, a young company designing innovative helicopters in Switzerland, a complete instrumentation system, in fact, the onboard instrumentation and also the ground equipment with the DAWs, the recorders, the transmitters, the displays, and all the processing aspect, so transmitter receivers, and all the complete set in order to cover their needs of instrumentation for their test campaigns. Here you have an overview of the architecture with the gray boxes called XMAs, which are the DAWs, the orange box in the middle, which is the Ethernet switch, then the recorder, and that can perform also acquisitions. Here in this case, it's the voice, pilot voice. And then it ensures, of course, the recording of all the acquisitions, but also the extractions of the measurement that has to be sent to the telemetry in PCM, to the transmitter, sent to the ground, to the receiver, the antennas, receivers, and all the ground recorders and the software, ground software to process all the data. One other example, one foreign military sales of the Black Hawk, where in this field we have also delivered a complete system for instrumenting this helicopter, but also it was the first time that we had an equipment mounted on the rotor head of the helicopter. So now let's focus on the IRIS project, which is a project funded by the European Community under the Clean Sky 2 program. It addresses the fast rotorcraft called the Racer, designed by Airbus helicopters. This fast rotorcraft, in fact, has 3 rotors. One main rotor here, which is classical for an helicopter, but something quite new is the 2 lateral rotors, which are called pushers, in order to achieve a very high cruising speed of up to 220 knots. And we have been, Safran Data Systems has been selected to design and deliver all the instrumentation of these 3 rotors and to provide an innovative system that we call the IRIS system, in order to be able to propose all the measurements, so 128 channels being acquired, a total transmission between the rotary part and the fixed part of the aircraft of 50 megabit per second, while in parallel offering a very accurate synchronization capability of 50 nanoseconds. So exactly the same kind of order of magnitude you achieve with a very efficient wired connection between your acquisition systems, your various DAWs in the system. So this was one of the main challenge. And the goal was to have a very efficient and very reliable links in order to achieve a totally error-free communication between all these 3 rotors and the main fuselage. So the components that we have designed for this challenge is first a DAU that is mounted on the rotor head, that is fully modular, so that can be scaled depending on the number of channels that you want to have on your rotary part. And this equipment is powered by an inductive system, a smart inductive system. So why it's smart? Because comparing to the legacy inductive systems, where you have a very low efficiency ratio, so you radiate a lot of energy out of the inductive system itself, and you have a lot of counterparts and side effects in your helicopters. Typically, it happens on some helicopters that the pilot completely lose the VHF link because it switched on the inductive system of the instrumentation. So it's a very, very heavy counterpart that affects even the safety of flight, because the VHF is absolutely crucial for the safety of flight. So this system has been designed in order to focus all the magnetic beams in order to have a very high ratio and avoid any radiating energy out of these two discs. They are easy to mount, unlike the slip rings that need to remove completely the rotor head. These are made of two moon-shaped parts that can be mounted, dismounted without any impact on the rotors. So it's very easy to mount and to dismount. And then you have a link on the stationary part with convert a standard 28 volt to the proper voltage and current needed to have a very efficient induction system. So the transmission, maybe it's in, yeah. For the data transmission, we have designed a wireless system based on two different radio technology that we are hybridizing. The first one is the Wi-Fi. It sounds very surprising to use standard Wi-Fi, but in fact, Wi-Fi is a large set of different modulation standards, frequencies, and so on. And we have performed a lot of tests in order to select the right one, the right frequency, the right modulation schemes, in order to cope with this very specific radio path, and especially also the blade masking induced by this kind of application. Wi-Fi is very efficient for data transmission. We use it every day, and it works quite well. And it's exactly the same thing in the system, provide the encryption scheme that is also efficient and needed for this kind of application. But it has a counterpart. It's not efficient at all. It's even quite bad for synchronization. And so we have added the impulse radio ultra-wideband to this radio solution in order to provide very efficient radio synchronization based on the PTP lag, the precision time protocol IEEE 1588 that you encounter on standard Ethernet communication. We have implemented this solution directly in the system, and we have merged, in fact, the Wi-Fi and the ultra-wideband in order to avoid the final user to have to manage all these antenna sets, and one dedicated to Wi-Fi, one dedicated to ultra-wideband. We have designed a Duplexer right here that merge, in fact, all the communications, Wi-Fi and ultra-wideband together. You have a single antenna, so it's for the final user, the test engineer, it's only one antenna to install on the rotor head, but in fact, it has two completely segregated bidirectional communication, Wi-Fi and ultra-wideband. So the DAU has been adapted due to this to fit the constraints of rotary parts, meaning that it is shaped be nearly cylinder, I would say, and also it has some weights, balancing weights that can be mounted, adjusted in order to balance perfectly the device and to minimize the intrusiveness of this equipment mounted on the rotor head. We have performed in-house very specific qualification tests to this system, especially vibration profiles that are very specific on the rotor head of helicopters, but also thermal aspects and also rotating test also. And what we have seen on rotating test, the radio links works very well, but you have to be very careful about exactly where you place your antennas. You need to really work with the radiation pattern of your antennas, and that's clearly in the DNA of our company to be able to compute efficient budget link based on all the characteristics of the radio path, and which is very tricky with the rotating aspect. And so in order to be sure that the link will be established and will be efficient every time, because at high rotating speed, you have clearly a high dependency of the antenna positioning to have an accurate transmission. This system has been mounted, the racer as presented earlier is not yet finished to assemble, but it has already been tested on H-175 helicopter. which has a similar rotor, in fact, to the racer. You have pictures of the installation. You have the dowel on the rotor head. You have here the inductive antennas mounted, and you have on the top of the, I don't know how to call it, the cover of the rotor. You can see the little antenna. Here you have the receiving antenna on the tail of the helicopter. And so test has been performed. The first flight test has been performed last June, and all the results are very good, and we are very happy, and the customer is very happy with the result. In fact, the one sentence that summarized everything, and for us it was our initial goal. The people that process the data, that have seen the data after the flight, they say, okay, it's exactly as if it was a wire connection. So that's exactly for us, that was our goal. So it was we are very happy to have this kind of feedback. And in fact, the data are as accurate as if it was a pure wire connection without any single bit lost during the flights, and having the data fully synchronized as if, once again, they were connected with a wire. So what's next? We will continue to improve this system. And typically, one first aspect, we call it the tunneling capability. We have somehow a proprietary link between the rotor head and the stator part. And we want to open this system to third-party solutions, typically IP cameras, for example, or in fact, any kind of Ethernet source that can be placed on the rotor head. And they can be connected to our system totally transparently and send the data through another data sink that will be on the stator part. Also, we want to increase the acquisition capabilities to not only legacy sensors like strain gauges, accelerometer, and so on, but also to fiber optic sensing. And in this respect, we want to cooperate with third-party companies and to add this capability to our system. We have already coupled, in fact, an external fiber brag interrogator to our system. It works. We would like to go further and to integrate this system directly inside the stack. We have now a movie. I don't know if we want to launch the movie now or maybe ask questions as you. I think it's better to launch. Okay, we have a little movie that will summarize and show you exactly what I've said on the IRIS project. Could be nice to have it on the screen. Okay.
L'aventure IRIS a démarré le 1er mars 2018 suite à la signature du contrat entre Safran Data Systems et la Commission européenne dans le cadre du programme Clean Sky 2. À ce titre, Safran Data Systems fait partie des 40 partenaires sélectionnés et coordonnés par Airbus Hélicoptère pour la fabrication de l'hélicoptère prototype Racer. IRIS est le nom donné à l'instrumentation d'essai innovante pour les 3 rotors du Racer. Et sa caractéristique première est d'être 100% sans fil, ce qui permettra de faciliter la mise en œuvre et la maintenance de l'instrumentation d'essai, tout en augmentant, en améliorant les performances intrinsèques. Une des clés du succès de l'installation d'IRIS sur le Racer était de pouvoir démontrer cette nouvelle technologie sur un hélicoptère conventionnel. Ceci a pu être possible grâce à l'hélicoptère qui est derrière moi, le H175.
Aujourd'hui, dans l'environnement des rotors d'hélicoptères, comment pouvons-nous, en utilisant une technologie sans fil, obtenir un résultat aussi fiable qu'une technologie filaire? Les défis sont nombreux. D'abord, il faut transférer un grand flux de données, environ 30 mégabits par seconde, et ceci sans avoir de perte de données dans la transmission sans fil, malgré le masquage des pales liées à la rotation.
Le système IRIS peut être décomposé à ce titre en 2 grands sous-systèmes. Un sous-système pour l'alimentation en énergie de l'instrumentation d'essai. Un boîtier va venir convertir le 28 volts présent sur la machine en un champ inductif. Ce champ inductif est transmis depuis une couronne fixe vers une partie tournante.
Cette alimentation doit être réalisée par une technologie sans fil et sans utilisation de batterie et inclure un système de télésurveillance de bon fonctionnement de cette alimentation.
Le deuxième sous-système permet la communication entre le boîtier d'acquisition installé sur la tête rotor et le réseau d'instrumentation d'essai qui est situé à l'intérieur de la cabine. Il y a une antenne positionnée sur le haut de la coupole de la tête rotor et une antenne positionnée sur la queue de l'appareil. Cette liaison sans fil permet de transmettre les données en provenance des capteurs.
Il faut transférer une grande variété de données, depuis des capteurs classiques comme les jauges de contrainte, mesures de température, vibrations, mais aussi des technologies plus récentes de capteurs numériques, voire fibre optique. Ensuite, la synchronisation. Toutes les données des 3 rotors, y compris aussi celles acquises sur le fuselage de l'hélicoptère, doivent être toutes synchronisées avec une précision de 100 nanosecondes. Bien sûr, le système installé sur les rotors doit être configuré par la liaison sans fil en se connectant simplement sur le bus Ethernet de l'installation d'essai en vol. En plus de ces défis techniques, il y a les contraintes environnementales et d'installation. Le système doit répondre à la réglementation DO 160 avec en particulier un point spécifique concernant les vibrations de l'hélicoptère. Ensuite, les contraintes d'installation et de tenue mécanique. Le système doit répondre à la réglementation CS29 appliquée au rotor d'hélicoptère, et ceci pour garantir la sécurité de la mise en vol. Dernier point, un tel système doit être utilisable sur n'importe quel type d'hélicoptère ou d'aéronef. À tous ces défis, à toutes ces contraintes, le projet IRIS développé par Safran Data Systems propose une solution technologique opérationnelle.
Les données sont envoyées à un récepteur gateway situé à l'arrière de l'appareil. Ce récepteur gateway transforme les données en forme de paquet Ethernet envoyé à un enregistreur. L'enregistreur enregistre les données et les transmet via un émetteur DTRDM à une salle de télémesure au sol.
Au sol, la réception est effectuée par une antenne Comtract couplée à un récepteur RX1 qui délivre le message chapitre 7 à l'enregistreur GMDR6 équipé d'une carte MTV-ME de réception. Le GMDR décommute le message chapitre 7 et transfère les données à la salle de visualisation suivant le standard Ethernet chapitre 10. Nos moyens de réception télémesure comportent 2 sites. Avant la mise en vol du racer, nous prévoyons la création d'un 3e site de réception. Les 3 sites de réception seront connectés via une liaison Ethernet au standard IRIC 218 à un best source selector qui effectuera le choix de meilleure source. À terme, les 3 sites de réception seront pilotés par la suite logicielle Maestro. Ces premiers résultats de suivi de vol en télémesure ainsi que les premières analyses de données après vol sont très prometteurs. En effet, nous avons ouvert l'ensemble du domaine de vol du H175 depuis le vol stationnaire jusqu'à des vitesses allant jusqu'à 170 nœuds. Et les premiers constats sont que le système IRIS n'est pas sensible aux conditions de vol. Concernant les vitesses de rotation du rotor, inférieures à 400 tours par minute, et les effets de masquage dus à la rotation des pales, là aussi, le système IRIS n'est pas sensible à ces phénomènes. Nous avons constaté que très peu de pertes de données dans la transmission. Évidemment, ces premiers résultats ne sont que le début d'un plan de maturité pendant lequel nous allons essayer d'explorer les limites du système, comme par exemple augmenter le flux de données transmises entre le rotor principal et le fuselage, ou encore les vitesses de rotation pour dépasser les vitesses de 2000 tours par minute. Ces essais de mise au point et de plan de maturité sont indispensables afin de lever tous les doutes possibles sur les résultats fournis par le système IRIS pour assurer les premiers vols du racer.
Thank you. Thank you for your attention. Do you have any question? Yes. I'm sorry, it's difficult for me to hear. Tu m'aides un peu là.
Is that okay? Yeah. We're looking at incorporating structural health monitoring systems into more fixed-wing components. And with that, it's kind of more ultrasonic transducers feeding into a central data acquisition unit. Would you be able to interface with third-party data acquisition units such as that?
Yeah, I see no reason why it would not be possible to clearly interconnect with such systems. So,
yeah. I think it's the question is whether you deal with third-party people or you build everything within house. Generally,
well, all our equipment are respecting standards. Okay, and we have people like Boeing or Airbus have developed their own modules to interface within our system. There are ways to do that. Okay. So it's a matter of cooperation between the design centers, your technicians and ours to do that. But this is something that we have already done for Boeing Commercial. We are doing that also for another program in the US I cannot talk about. I'm not supposed even to know about myself, but it means so. I'm curious sometimes. So. And we have done that with Airbus too. Yeah. It's our products are evolving all the time. Okay, and it's very important that we get backward compatibility also. So it's really improving, adding features, with keeping the system open as far as we respect the standards.
And yeah, clearly the data format, the packetization, the header trailers, the way to send the data, to receive data from an external third-party system is, in fact, it's our everyday life, and it's clearly not the area where we encounter the biggest challenges. The biggest challenges is mostly on the environments. Here, clearly the data links, all these aspects, but being able to adapt the data format to be configured by a third-party software suite, because the format is another one, the one we have natively in our systems, or being able to deliver the data to another tool that was not even in the scope of our initial specification is clearly something that we encounter, and we adapt on that quite easily. I have not encountered any situation where we were not able to propose something. So it's yeah, for me it's not the biggest part of the challenge. It needs to be clearly worked on the study on facing the real specifications of what has to be done, but I don't see any major challenge in that.
Okay, thanks.
You're welcome. Yep.
Thanks, Tom. I have a question regarding the video, a technical question. It was shown that the power transmission is done inductively, and batteries are an issue, of course. We know batteries are always an issue. Are there any means for small power outages like supercaps or so in the system? Or is it 100% reliable, that inductive power transmission?
Yeah, today the first 30 flights and so on have demonstrated that we have reached a very high level of efficiency in terms of power transmission. The theoretical efficiency ratio was something about 80 or plus, and mounted on the rear rotor with all the metallic parts, because the challenge is clearly to avoid to have a side coupling with all the metallic parts of the aircraft by itself. And the ratio was better than 50 or 60%, which is still very good compared to the typically 20% that was achieved in the past. So 80% of the energy was radiated in the helicopter structure by itself, or avionics and so on. So the efficiency is very good, and we have also introduced in this inductive system real-time monitoring, that's mentioned, but it was quickly mentioned, and I forgot to tell it previously. And in fact, it was a clear requirement from the final customer to say that I want to be able to monitor which quantity of energy you radiate and which quantity of energy you receive in real time for every situation, every flight profile. I want to be able to know exactly this, and this is performed autonomously by the inductive system that has also somehow a radio data link, digital communication in addition to the pure inductive system. And so it's that's why we call it a smart system, because there's a kind of loop back for the control in order to ensure first to report to the flight test engineers and what is in real time the efficiency, but also to report if the system is okay. And in case there's a failure, in fact, we are able to report, and maybe the flight test engineer is able to stop everything just to avoid to radiate the data. So far, we have not encountered such situation. It's true that batteries or supercap could be an option also, but in fact, the customer is quite happy. In the original specification, to tell you the truth, it was a plan to have such a thing, but the weight or the constraint, they were very happy to be able to remove that because placing more weight on the rotor head is always tricky. And but what we have in mind as an extension of the system today, on some helicopter rotors, you have already a 28 volt. So we plan to have, because of de-icing system or some other avionics systems that are already on the rotor head. So we plan to have this system also available for standard 28 volts. So even if you have already the power supply available on your rotor head, you don't need to have all this inductive system. So it's a modular system that will be able to adapt. So today, I would say if the 28 volt comes from a battery, or if it comes from energy already available for the operations of the helicopter, we don't really mind about that. And if there's nothing, we can propose inductive system.
Thanks.
Any other question? No? Thank you very much.
Thank you.